Welcome back to my Devlog series for a strange new genre I'm working on. This video is going to be a bit different from usual, as I'm going to need to invest quite a bit of time into a new core system for the game before I have any visible results. For now, let's go over the more visually interesting parts, and maybe you'll decide to stick around and get down into the weeds with me later. I would never say I'm a great 3D modeler, but feel free to judge me harshly anyway. As those of you in the Discord or who follow me on Twitter may already know, I spent maybe about half the time since the last video modeling this monstrosity. Actually, I might need to apologize to the creator of the M1941 Johnson, since he specifically designed it to be recoil operated, believing gas operated designs to be inferior. Since my next goal was to implement gas operated weapons, and I love this thing's unique design, I took it upon myself to add a gas block. Alright, enough about my sins against history. Let's pop this baby open and see how she works. Or at least we would, if life was easy. Instead, I came up against two choices, both of which give me a headache. But I'm glad I ran into this problem, as this is exactly why I'm exploring many different weapon designs before running ahead and half-assing a bunch of other mechanics. If we take a look at the way the hammer moves in this shot, it's fake, I guess. I mean, everything in games is fake. This is just more fake because while it's true that the hammer moves forward because the latch attached to the trigger moves back, you'll notice that when I release the trigger, the hammer comes back for no reason. This is because the current system allows me to bind the positions and rotations of components directly to other components. This worked really nicely on my other test designs, which only needed simple movements and have very few active components. But there's a lot more going on in this one, and I can already tell the current system is not going to scale into the puzzle style that I want. It would be very easy for the puzzle to devolve into plainly animating stuff you'll never see while playing, rather than feeling like you've designed a functional solution to a problem. So programming animations out. What is option number 2? Here you can see I've converted the weapon to a skeletal mesh and set up physics for the different pieces. This is insanely finicky just to set up initially, and ultimately unpredictable at different strengths and speeds, not to mention different frame rates. Given that the forces inside of a gun are extremely fast, and just imagining trying to explain all of these physical parameters to a player makes my head hurt, this will not end well. And those were the two options. Both of them suck. End of project, folks. See you next time. But wait, what if there was a third option that only half explodes my brain? Now, I'm still investigating this, but I might just be able to get away with not having to build and modify the engine directly to do this one either. I would also appreciate if anyone out there can fill me in on any problems or inherent limitations with this algorithm I'm about to discuss. Oh, and if you know how to fix them too, then shoot that my way, please. I'll start from the basics because I believe you only truly understand something if you can teach it to other people, and I want anyone to point out if I got something wrong at any level. So, we can make any visual mesh we want, but how do we simulate pushing it around the world? In Unreal Engine, we've got about 4 options for this: spheres, capsules, cubes, and convex shapes. The first 3 are very basic or primitive collision shapes that are relatively easy to calculate when they overlap. For a sphere, we can see that it overlaps with something whenever its distance to that thing is less than its radius. Similarly, we can think of a capsule like stretching out a sphere to be infinitely many spheres along a single line. This means we can find the closest point to something on that line and simply do a sphere-style test there. A cube or cuboid overlapping is also straightforward. Just answer 3 questions about the closest point on the other object. Is that point's x position inside the cube's width? Is the y position inside the cube's height? And is the z position inside the cube's depth? If even one of these is not true, that thing will lie outside of the cube. For convex collisions, things aren't so simple. So if you want an explanation of how these work, just watch this short 30-minute video. Not simple, but not ridiculously hard either, but obviously this will cost extra processing time. What is ridiculously hard are more complex shapes with extreme internal angles or holes, which all of these rifle parts just so happen to have. And you'll notice we already used all 4 of the options the engine gives us, so what can we do about it then? Well, we simply spend 20 plus hours manually cutting these awkward shapes into nice convex holes so the engine doesn't choke to death. Okay, we know how to make arbitrary shapes smack into each other and the engine pretty much does everything for us, so problem solved, perfect simulation, right? Well, yes and no. We can see from the physics asset version that we're getting perfect collisions, but remember that actual physics is inconsistent and not so easy to control. What we need is something that will be puzzle friendly, meaning tools easy enough for players to know what will happen when each one gets hit by something, but also when tied together in a big chain, produces fun to watch, convincing, and complex interactions. And Unreal doesn't give us a way to replace the physics of random components with something else. Well, nothing I'm aware of anyway. We can ask the engine if we're going to hit something, but the only way to do that is through line trace, sphere trace, and other similar functions, which are useful, but are never going to give us great results for arbitrary shapes. And yes, I hear you there in the back row, just enable sweep when moving components. If only things were so easy. No, the engine won't collide components that are inside the same actor. And there's this little note that's been attached to the rotation function for how many years? Yeah, the engine gives us zero solution for sweeping rotations. So we're going to have to go deeper. It's finally time to dive into some C++ again. And down here we can find some very interesting functions, such as component sweep multi, which takes the collision holes from a component and moves them along a vector until they hit something. I envision sweeping similarly to how we said a capsule is like an infinite set of spheres placed on a line. So let's imagine the engine smears our shapes along some vector and stops as soon as it hits something. The most important thing this function does for us though is tell us the location and direction in which the shapes collided. Cool, but what about rotation? Well, not just rotation, but actually scale as well. This function takes our shape with a specific rotation and moves that through space, and as far as I can tell, it seems to completely ignore scale. Maybe we can get away with not scaling our objects, but we're going to have to implement rotation sweeping manually. The further down I go into these calls, the more of the engine's core physics stack I'd have to modify. There's no magic one-line fix for this. So in the interest of keeping maintenance costs low, I'm going to make my own version of the component sweep function that steps through the change in rotation and see how bad the performance is on that. Let's assume all that works. Now we just need to do something when parts touch, since real physics sucks. So the final piece of this puzzle, no pun intended, is what I'm calling motion solvers. Each motion solver will handle one specific kind of motion, and players will be able to attach these directly to parts. When parts get hit, these solvers will read the motion for whatever hit them, and then convert that into their own output motion. Here's a rundown of which solvers I've got on the list so far. The slide will be able to take any motion that aligns with its vector, and then move itself along that direction. The lever is kind of the opposite of the slide. It takes any motion not aligned with its vector, and then rotates itself in that direction. The gear type is going to probably explode into a bunch of different gear subtypes, but mostly they turn input motion into rotation. The latch and catch, or maybe hook and nook, will allow locking motion in one direction when specific locations are hit. The ramp is a bit different. It needs to make the thing that hit it rotate instead of moving itself. And finally, the most dubious one on the list is channels or holes. This will need to be like negative space that kind of pulls things that hit it into alignment with the direction of the hole or channel. Moving on to the other kinds of components that will make up the puzzle interface, we'll definitely need more things eventually, but right now I have planned out springs, pressure chambers, and axles. Springs are probably the main way you'll get stuff to move to where you need it to be. Pressure chambers will be driven by the internal ballistics simulation, and axles will let you modify the pivot point of a component. For example, this shape's pivot point is here, and it rotates like this, but if I change the pivot point, then it rotates totally differently. Alright, we're almost there. Just a super technical section left and we're done. Let's end with a run through of the complete algorithm. First of all, we need to create a motion manager actor component. Then we'll add two functions, solve location and solve rotation, which need a primitive component and the motion delta to evaluate. We'll use these two when changing the location and rotation of our mesh instead of the typical set, relative, location, rotation functions. we'll also have a function that associates a motion solver with a mesh, and we can add as many as we want to a single mesh. Of course, that means we need a motion solver class too. We'll want the motion solver to be a type of scene component so we can give it space and direction easily. We'll just add one function on it for now, which tells us if we should use this motion solver or not when we get a hit. Now let's assume we've already built a weapon compatible with this algorithm and see what happens when we pull the bolt back. Step 1. We collect all of the component's child components that can't move and use those plus our own holes when we're sweeping. This is because when we move an object, we will automatically move its children as well. Next, we sweep our collection of shapes until we hit something. If we moved less than our target motion delta, must mean we have a collision. Before we do anything else, let's go ahead and move our shape to match the collision location and remove this distance from our original motion delta. If we hadn't hit anything, then we would stop here. But we did hit something, so next, we find the best matching motion solver to use. This will be based on things like the impact location and direction of the impact normal. Then we call the solve function on the thing we hit. This means we start all over again at step 1, but now we're working on the thing that we hit instead, which might hit something else, and then that thing hits something even more else, and so on. There are 3 ways out of this infinite chain of parts pushing each other. 1, we reach the part's limit on range of motion. 2, we hit something that can't move. Or 3, we don't hit anything, so we finish the whole motion. Eventually the chain works its way back up to us, and we can continue on to check if the thing we hit moved out of our way. If it did, we go back to step 1 and try to finish our motion. Otherwise, we must be stuck, so we're done. Hey, speaking of stuck, you stuck it out and made it this far into the video. I know I couldn't listen to me ramble on like that. Well done. Anyway, let me know what you think in the comments of the Discord, and maybe I'll have a less technical video for you next time.